we'll be talking about picking flowers here. So I thought first I would warn you that you may get in trouble when picking flowers. So if you find yourself somewhere in Britain, you may end up with 5,000 British pounds of fine if you pick the wild flowers. And apparently, when it comes to picking flowers, there are the laws which regulate this. There are two categories of these laws, and if you don't want to pay a fine, you'll probably want to know the rules before you start. So that's what we will try to do here. First, you want to get to know the laws, and you want to get to know the restrictions that they impose. And as a real rascal, you will want to find the loopholes, right? So we want to see how we can sort of circumvent some of the problems. Then you want to develop a method. And you may even write a wiki page. I was surprised to see that there is one on how to pick flowers. So there is even a wiki page on that. After you have done that, you want to choose your tools, right? So we will discuss a little bit about the tools of the DFT or flower picking. And then hopefully after this workshop, you will be ready and you can do the real calculation. Yeah? Okay, so how do we calculate the material? This is what we want to do in the end, right? We want to take a material, we want to calculate its properties. So, for example, we want to know how to calculate lattice parameter and bulk modulus and phonons, electronic bands, magnetic properties, whatever you like, from first principles. So, what does it mean? If you go to Wikipedia, then you see that in physics and other sciences, theoretical work is said to be from first principles or ab initio if it starts directly at the level of established science and does not make assumptions such as empirical model and parameter fitting. Okay, so this is just a bunch of nuclei and electrons, your material, right? And since there is probably nothing that comes second to the quantum mechanics, then this must be the first principles theory that we will base all our calculations on. So what do we have to do? We have to solve a Schrödinger equation. Yeah? So we have a Hamiltonian, and we want to calculate the energy, and we want to get a wave function that describes our material. And then, well, let's set up this Hamiltonian. We know what goes in. Here we have the kinetic energy of the electrons. I think this is the electronic part first. Then we have the interaction of the electrons with the nuclei. We have the electronic interaction, so electron-electron interaction. Then we have the kinetic energy of the nuclei and their interaction. The wave function depends on the positions of all the electrons and all the nuclei. Okay, so you can see it. This is a many-body problem. And, well, if you are in the case of one atom, this may be solvable. Even in case of two atoms, you may get very lucky and do some miraculous work, and then you solve this. But what do you do in a solid? Yeah, this is becoming pretty tricky. So, what shall we do? Well, this question was answered already almost 100 years ago by Dirac, who said in 1930 that the general theory of quantum mechanics is now almost complete. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole chemistry are thus completely known. However, exact application of these laws leads to equations much too complicated to be soluble, and what we need are the approximate practical methods to avoid too much computation. Okay, so let's start approximating. The first approximation you can think about in one such many-body system is the adiabatic approximation. So you say nuclei in this system are heavy and they move much slower than the electrons, so the electronic cloud has sufficient time to relax to its ground state at any instantaneous configuration of the nuclei. So what that gives us here is that we get rid of this term, which basically depends on the nuclei. Now the positions of each nucleus enter the wave function as parameters. And, well, what we need to solve is the electronic Schrödinger equation, where we have taken that all the nuclei are fixed. Okay, so this is good. Now we approximated something. Now let's see how much storage do we need for a calculation with this approximation. So we will take an atom, for example, nitrogen with 7 electrons, and we decide to store the wave function. So we store 10 values per coordinate. What do we have? So this is then the wave function. We have 21 coordinates. So say that, as I said, we store 10 entries per coordinate. That is 10 to 21 entries. And now, say that we need 1 byte per entry to store this. And then think about how much, storage this is. So on one DVD, you have about 5 gigabytes. So that means that you need something like 2 times 10 to the 11th DVDs, and then take a weight of 10 grams per DVD, then this, weighs approximately 10 to the 6th tons of DVDs. So now you may ask yourself, is this a lot? I have no idea how much this is, 10 to the 6th tons. But then, there is a web page which tells you how much something weighs. So this weighs like 6 times Empire State Building. So, and this is only for storing the nitrogen wave function. So you probably don't want to do that, yeah? Which means our approximation is, well, not enough, right? So we have to start from the beginning, yeah? Okay. Here we were. Born-Oppenheimer approximation. We have the electronic equation, and now let's try to imagine a system in which the electrons are independent, so they don't interact. Okay? So what we are left with is this part here of the Hamiltonian. So how does that help us? Well, it actually does, because you can see here that this Hamiltonian then is basically a sum of one-particle Hamiltonians. And be careful, I'm saying one-particle Hamiltonians, not one-electron Hamiltonians, because we have made all of these approximations and we assumed independent electrons, okay? They don't interact here. Very well, we have now this nice, small, elegant Hamiltonian. And what you can do is take a Slater determinant and calculate an observable, calculate energy here. Okay, so what you actually will see after some writing out of this expression, what you will actually see is that to calculate energy, you only need the single particle orbitals. These are these psi i's that enter here into the Slater determinant. Okay? So for any observable, you will only need single particle orbitals. Very nice. Okay, so back to the nitrogen atom now. Let's see how much disk space now we need. So with 7 electrons, you want to store, again, 10 values per coordinate. But with 7 electrons, you have maximally 7 orbitals, right? So psi1 to psi7. Now each orbital depends on three variables, right? X, Y, Z. You have 10 entries per coordinate, that's 10 to the third entries. And in total, for all orbitals, you need 7 kilobytes of data. So this is kind of very nice approximation, right? So we managed to do this because we assumed that the electrons did not interact, right? They are independent. However, they do interact. So is this important at all, what we have seen so far? Well, that's where the mean field theories come in. So what we want to do here is to try to find a way to map this interacting Hamiltonian onto a non-interacting one. And so we want to pretend that we have a system of non-interacting particles with some effective potential which might include this interaction, right? And then we land with the mean field approximations, essentially. So basically, each electron sees the potential as produced as some mean field produced by all the other electrons, right? So in this mean field approximations, you have already met, for sure, Hartree-Fock, and density functional theory is what we're doing here. So let me remind you, so the first idea, or first ideas, they were developing approximately at the same time. The Hartree-Fock and the DFT, the initial DFT, let's say, was actually here found by Hartree. What he says is, okay, let's say that the potential consists of an external potential due to the ions, and we approximate the true electronic potential, and we say each electron sees the others as a smooth distribution of negative charge with charge density rho. Okay, so this is basically what is written here. So you will find the charge density like this, coming from all the other electrons. And then you will have the electronic part of the potential written out like this. And then you will have also the external potential coming from the interaction with the ions. So you see that here, right? Very well. So now we can come to the Hartree equations, where you see that, well, there is one for each occupied one electron level, and this is essentially what you see here. They are solved self-consistently. For a trial electronic potential, you determine the one electron wave functions, and then you use them to construct the new potential, and then you iterate further. What you see here is that you have the external potential, and you have the interaction of the electrons with each other through the Coulomb force. However, something is missing, right? So Hartree equations can be derived from the trial function, which is basically a product function of the one electron or one particle wave functions. This product function is not asymmetric, and this is a problem because this is required by the Pauli principle. So you can use the Slater determinant instead, and then you arrive to the Hartree-Fock equations that also contain an exchange term. So this is this part here. Okay, so now we have a very nice, complete set of equations that contain everything. what we have is that, well, these Hartree-Fock equations, they are wave function based, right? You have the psi, and then you have to optimize the energy. It leads to many complicated wave functions. And essentially, you want to try to extract information about physical systems with an integrated quality instead. And this is where the density-based methods come in. So what you want to do is use the density. You see it is defined here. And then you want to minimize the functional. So here we have the energy, which is the functional of the density, provided that it exists and that it is to some extent known. So the essence of DFT is essentially stated here in these theorems of Hohenberg and Kohn. Although the basics of DFT have been established also earlier, but it was not until Hohenberg and Kohn postulated this, have proven these two theorems, that the DFT actually started being really used and developed. So theorem 1 says that for a given external potential V, the ground state properties of a system are uniquely determined by the electron density alone. So they're functionals of the density. So you have the density, you can determine everything if you have a potential V. And the second theorem says that the exact ground state density minimizes the energy functional E of n. Okay, so now we have the theorems, and now we want to know what it is that we actually need to solve. How do they help us solve our problem? How do we use DFT to calculate materials properties? So, first of all, let's start from non-interacting electron gas. You remember that this is very convenient. In a potential Vs, this will be single particle Vs. So, we will get one electron Schrödinger equation. That's how it will look. It is pretty simple, right? We have the kinetic and potential energy term, where this is some effective potential. Not yet. This is non-interacting electron gas, so we don't need anything effective. So for n electron states, now we construct the one particle electron density from the lowest lying one particle states here. And then you know that for small variations around the ground state density, energy is stationary. So here you will see that if you, from this fact, you will get the exact ground state density corresponding to Vs. Very well. Now we have to go to the interacting system. And, well, we assume that we can find an effective potential Vs, so that, this is the key point, that the density of one particle state, one particle density, let's say, equals to the true density in the ground state. Okay? True meaning, the density of the interacting system. So that means you will get this energy functional, where you will have featuring the kinetic energy of the non-interacting system. Then you will have the external potential coming from ions and whatnot. Then you will have the Hartree term. And then here, in this term, which is called exchange and correlation, you will have the exchange interactions and the corrections to the kinetic energy, because this is the kinetic energy of the non-interacting system. Okay? So now, again, you know that the energy has to be stationary around the ground state for small variations of the density, and then you can see what this effective potential corresponds to. So you end up with a set of Kohn-Sham equations with an effective potential, and they are solved self-consistently, which means that you can guess this potential you can calculate the single particle orbitals, and then you can calculate the density, and then you plug that back in, and you iterate until everything converges. So now everything here is fine. So if you are given a density, then you can calculate the Hartree energy, and you can calculate the energy coming from the external potential of the nuclei. And this one particle kinetic energy can be calculated if we know Vs. However, there is still something that we don't know. So these terms we know how to calculate. This guy here is a problem. All right? So, you know, we're back at the beginning. We have a problem, and we have to do something about it. And we do what the physicists always do. Well, you know, we have to approximate again, right? So what you want to try to do is, well, find something that makes sense for your for this well, system. What can you do? So the first approximation that was suggested in this case was the so-called local density approximation, or LDA. And, well, basically, the idea is pretty simple. It exploits the nearsightedness of the electronic matter. And what you need to do here is calculate it by using the exchange and correlation energy per particle of homogeneous electron gas. So what does this mean? At every point in the system that has an actual density, well, you will not be able to calculate the exchange and correlation energy functional, but you can take this point, you map it to a homogeneous electron gas with the same density of this point, right? For this, you can calculate exchange and correlation energy. So the exchange you can calculate analytically, and correlation you can calculate using quantum Monte Carlo. And then you can take this value and try to approximate the actual exchange and correlation functional. Okay, so it would be like, you know, making a picture out of small pieces that correspond to a homogeneous electron gas. Okay, it seems pretty crude as an approximation, and well, you know, you cannot blame Kohn and Sham, who said we do not expect an accurate description of chemical binding. Well, this approximation has been, well, the working horse of DFT since basically it was established, and it is giving fairly good results. You can, of course, improve it. Yeah, you can improve it, and you can incorporate some exact constraints successively. You can start with just density dependent, and then you can include the gradients, and you go to GGA, or generalized gradient approximation, you go to some meta GGAs, exact exchange, and so on. So this is what is usually referred to as Jacob's ladder in the DFT. Okay, so in any case, about this, about exchange and correlation functionals, you will hear more on Thursday in the lecture by Matthias Redis. Here I want to say something more about Kohn-Sham, because a few cautionary notes, right? So Kohn-Sham orbitals, when you get them, they have, strictly speaking, no physical meaning, okay? So except that, of course, you can calculate the exact density of the interacting system from them. Yeah? So in particular, this determinant is not to be taken as an approximation to the many-body wave function. And likewise, the orbital energies have in general no physical meaning. Okay, so you have to be careful. Of course, you know, these orbitals or these orbital energies are frequently used. You see them in band structures. This is what we calculate, right? But you have to be quite careful with them. You have to be careful to know what is in, which approximations you have put in, and how you handle the whole thing, okay? So think about that. So the Kohn-Sham equations are solved self-consistently. You can solve the electronic part. You guess initially the charge density and the atomic positions that enter as in the external potential. You calculate the potential, then you will hear a bit more about this diagram later on. You have to set up the Hamiltonian, you solve the eigenvalue problem, you can calculate the Fermi energy, you calculate the output density. And then you have some criterion. Is my output density sufficiently close to the input density? If yes, then you're super, then you say everything is converged. I can now calculate the forces, and if the forces are not sufficiently small, that means I have to move the ions and I can calculate the new atomic positions. So if everything is fine and the forces are small enough, then we say this is also converged and you're done. However, you can have the state of an unconverged system wherever you want. So at this point, for example, if the input and output density are not sufficiently close, you have to mix the old and the new density, and then you have to go back into this electronic self-consistency cycle. Once this is converged, you can calculate forces in your atomic positions. They might not be converged, so the forces may be large, and then you have to go back in here again, move the atoms to the new atomic positions, and then you have to go through the self-consistency cycle for the electronic part again. Okay, so far so good. I think, well, these are the basics of the DFT, which you probably already know. This was just a reminder. And now, you know, there are different ways of how to tell your computer what to do. Yeah. So yelling obviously doesn't really help. So what you can do is turn the Kohn-Sham equations into matrix equations. This is what the computer understands. So you have two options. You can go either to discrete real space grid, or you can make an expansion of the relevant properties, so wave function, potential, and so on. You can use a basis set to expand them. So let's first see how it works with discrete grids. This is the one-dimensional illustration, so you have any function on a discrete grid. You have a set of points where you have the values for this function. This h is the distance between the 2 points. Now your function is a vector, and well, the derivatives you calculate as finite differences. For example, here you see the simplest formula for the second derivative in, well, the first approximation, right? So now if you want to go to calculate the Kohn-Sham equation, then it basically takes form like this. So this is the first entry, the second entry, the third entry, and then all the others are shifted by 1. So you have x1, x2, that should be x3, and you go all the way to xn. So this is sort of, you know, you have one chunk at the diagonal of this matrix, and then you multiply this by the wave function, which consists of this single electron wave function at each point here. Now you will notice that here we have also the points x0 and xn plus 1. This is because this is a differential equation and we need some boundary conditions. And now these boundary conditions have to be chosen such that, well, they make your life simple, and you want to choose them such that, well, they correspond to the real system and not to something else. Right? So for finite systems, the Kohn-Sham orbitals have to be 0 at the boundary. For periodic systems, well, you need these periodic boundary conditions, right? And then the integrals are calculated also as finite sums. So this is all something that a computer understands and can easily handle. But of course, it introduces an error by discretizing the functions. And it depends, obviously, on the spacing of the grid points. Okay, so the second approach is an expansion into basis functions. So you can choose some functions, phi mu of r, and then you can expand the wave function, right, with some coefficients here. This is the number of the basis functions. Then your differential equation that you started from will turn into a linear algebra equation, where you will have here the elements of the Hamiltonian matrix. Here are your coefficients in the expansion, and here are the elements of the so-called overlap matrix, right? And then you can write this in short like this. Yeah. Okay. So Hamiltonian itself contains the matrix elements of the kinetic energy here and of the potential, and the overlap matrix looks like this. Yeah? So it is diagonal for orthogonal basis functions. This is sort of obvious to see. Now, the choice of the basis is something that you have to think about in advance before you tackle any problem. It depends on two criteria. So first one would be the boundary conditions. So for finite systems, you want that at infinity, your basis functions are 0. For periodic systems, it is sort of very simple choice. You can use the plane waves. And the second criterion in the choice of the basis functions is generality versus the suitability to the specific problem, which in other words means the closer the basis functions are to the actual Kohn-Sham orbitals, the fewer basis functions one needs. So if you would be able to guess a basis function that equals the wave function, then you would only need the single expansion coefficient. That would be kind of neat. However, you also cannot choose a different basis set for each problem, right? So this is where this generality comes in. So you want to have sort of basis which can be applied to different problems. So there are some examples here. One would be the local basis sets. So you would use the local basis sets when you have some systems which are isolated, like molecules, atoms. Here you can construct the basis functions that are centered at the atoms. For example, in Gaussian methods, you use the Gaussian basis functions. You have in here the atomic position, so you really can center these basis functions at the atoms, so if you have more. There are usually linear combinations of such Gaussians that are used. The second type is the Slater type. So these functions have the correct behavior. They decay exponentially for large distance, and they have the correct behavior close to the nuclei. Right, so this is the Slater type thing. where this n is the principal quantum number, and again you have the positions of the nuclei, with an angular part, which is usually spherical harmonics that you can use. Okay, so what if we have an infinite system? We have plane waves for periodic systems, right? So this is our first choice that you could think of. It has several advantages. So one is that this is an orthonormal basis set. You have the single convergence parameter, which is the number of the plane waves. They are momentum eigenfunctions, which means that the kinetic energy is diagonal. And they also easily fulfill the Bloch einsatz for periodic systems by taking this wave vector here to be the Bloch k plus some reciprocal lattice vector. The potential matrix elements are then given by the Fourier transform of the potential. This is also sort of nice. However, one should also think about the potential problems that you might have with a particular choice. Okay, so this is the non-trivial part of this story. First part, or first problem, is that the ionic potentials have an integrable pole at the position of the ions, in which case you can use Gaussian and Slater type orbitals to solve this integral analytically. But if you are using grids and plane waves, then you have a problem, right? You will need infinitely many grid points or plane waves to describe this pole. So this is what you see here. So this is the ion, and you have this dip in the potential. The second part is that you have the core electrons, which are usually very localized. They are close to the ion. And localized functions need always finer grids, or they need more plane waves to describe. While at the same time, these core electrons are really doing nothing. Yeah, so they are sitting in there and not moving much, and they don't participate really in the binding and general electronic behavior. Right? So these would be the core states in this picture here. You may end up with some states which are close enough to the valence, and then they are called semi-core states. They have to be taken care of specifically, and I think that you will hear about that from Gregor later on. And then, of course, what you're interested in mostly are the valence states. All right, so these are the ones that you really want. So how do we tackle this problem? So there are essentially two possibilities. You can either use the pseudopotentials, which means you modify the potential to make it easier to treat. So you kind of remove this singularity. Or you can use, for example, the augmented plane waves. This is what you will be doing at this workshop. And you can treat the core and valence electrons differently. And this is a very convenient way, and this is, well, what is essentially an all-electron method. In the case of pseudopotentials, you kind of forget about the core states, or you actually include them into the pseudopotential that you will produce. So, as I said about augmented plane waves, you will hear more about them at Gregor's talk a little bit later on today. So let me just tell you what is the idea behind the pseudopotential. So for one thing, as I said, you have this singularity. So you have infinite potential at the position of the ion, which leads to the strongly oscillating wave function. And you would like to get rid of that. So what you want to do is replace this all-electron wave function by some pseudo wave function. Here, this is this psi tilde. It will be a smooth, nodeless wave function. You will require that it is the same like all electron wave function outside of some core radius here. So this is this RC here. And inside the core radius, you should be careful, this nodeless wave function is meaningless. Okay? The second part is, well, that's how you construct the pseudo-potential. You remove the 1 over R singularity. So this is now your pseudo-potential, V tilde. Therefore, you remove all the numerical difficulties and you create a smooth potential. So that seems to be all nice. Of course, if you are interested in the core states and well, their influence on the whole story, then well, this will not help you very much. In that case, it is much better to go to the augmented plane waves, where the basics are outlined here. So what we have is, in that case, we make something that is called the muffin tin spheres. So these are the spheres around every nucleus, where potential is spherically symmetric. So you can use the solutions of the radial part of the Schrödinger equation in this area. And then you have the interstitial, where potential is basically small. There is not much compared to the area close to the nuclei. And here you can use the plane waves. So as I said, Gregor will tell you more about it. So I will summarize here. As I said, we're solving here many body problems. They are difficult to solve, and you need large memory. You have seen how much memory you need for storing the wave functions. Therefore, you need approximations. For this, you already know about Born-Oppenheimer approximation, and then we have also seen what mean field approaches do, so Hartree-Fock and DFT. The essence of DFT is here, so if you are given an external potential, then the ground state density uniquely determines the ground state properties, and it minimizes the energy functional. Kohn-Sham equations are then used to map a system of interacting particles onto a system of non-interacting particles with the same density. Then you need to make some more approximations. They are made to the exchange and correlation functional. They are necessary. And then you seek a self-consistent solution to the Kohn-Sham equations. You have seen that various computational methods exist. You have to make your choice depending on what you want to calculate. And now I see critical look on Daniel's face. I have to say at this point that, of course, all electron FLAPW methods are the best, right? The best choice. Okay. So thanks for your attention.